Last class we started up to alpha nitrosation. So let us continue further. There is one more small topic which is about alpha beta unsaturation kind. And if you understand that part, then we can go into aldol and Cannizzaro reactions. Got it? So let me explain this next part, which is seventh part here. Seventh reaction that is about addition of alpha beta unsaturation. Alpha beta unsaturation. Okay, what does that mean? Suppose if you have, you know, a double bond like this, a double bond here. One second. Close it. Perfect. So if you have a double bond here like this, okay, so then this will be alpha and beta. So this is alpha beta unsaturated aldehydes are ketones. Got it? So if alpha beta unsaturated group is being added by some electrophile and nucleophile, we would be able to get products like this where oxygen is connected to H and here you will get Y this way. Or we can also get product like, you know, um, first we will have a double bond here, O and H here, and addition group will happen at Y here. So see the numbering wise, if you notice this is 1, comma 2, 3, and 4. 1, 2, 3, and 4. So the first type of an addition is called as 1-2 addition because it is added on 1 and 2 positions here, while this is 1-4 addition. Now, this 1-4 addition, because it is in an enol form, it will remain unstable. So it would get, it will convert back into keto form. So this is also eventually we call it as 1-4 addition product. Got it? So this is the 1-4 addition product here. Now, usually if you have to make such reactions, and suppose I have a double bond here, group here, this way, and imagine if at all I have to add something like HCN. Okay, if I'm adding anywhere from minus 70 degrees to minus 20 degrees Celsius here, it has been noticed that the major product for this case is basically OH and CN. This is found to be major product, which means it is 1-2 addition product. 1-2 addition product. While if I take the same reaction here, but I keep the temperature here around 100 degrees Celsius. So in that case, you will have this as OH with double bond here and cyanide, which will get tautomerized to get ketone here and cyanide here this way. So which is 1-4 addition. So it is clearly suggesting that when you're operating at very low temperature, this position is taking up the nucleophile much more comfortably as compared to this position. Okay. So this particular product is what we call it as kinetically controlled product. Kinetically controlled product. While the second one is thermodynamically controlled product. Now, between these two, how do we decide? Basically, in a conjugated form here, we have we have one pi star orbital here. So this is one pi star orbital, and at this double bond here, also we have one pi star orbital like this, like this. This is one pi star orbital, correct? So if you notice, the charge on this pi star is higher. So if you notice on this position, one, two, three, four position. So I can say the pi star carbon 2 has, at second position, has more polarity than pi star at fourth position. And that's the reason why if a nucleophile has to make a fast reaction, a nucleophile will always choose 2. But if a nucleophile is not worried about whether the reaction goes fast or slow, but if the nucleophile is more worried about I should get a more stable compound, then it will always go for 4. So it all depends upon strength of nucleophile. So strength of nucleophile. So if it is stronger nucleophile, okay, they prefer uh, pi star 2 position. If it is weak nucleophile, weak to good, weak to good nucleophile, they prefer pi star 4. Got it? So that's a way. In some cases, you would notice that we will have 1,4 addition, or we will have 1,2 addition. So it all depends upon from which position it is attacking, all right, and what type of nucleophile it is. If a nucleophile is weaker or neutral molecule, they generally prefer to go for more 1,4 addition than 1,2 addition. Okay, so this is the way you need to judge in which case what will happen. All right. Any addition which happens at 1,4, correct? Addition that happens at 1,4. Addition at 1,4 positions on alpha beta unsaturated aldehyde or ketone. We call it as Michael's addition or Michel's addition. Michael's addition or Michel's addition. You can call any one of that. So this is what would happen. Clear? Let me show you a few examples. Whether it is only restricted to, I meant to say, whether it is only restricted to certain type of reaction or we can have it in any cases. So that's what we will see. First, I'll show some Michael's addition cases here. So most of the Michael's additions, we expect this to happen with an active methylene position like this. So suppose if you have double bond O this way, and I'm treating this with ETO minus, ETO minus Na plus. Okay. So what do we expect? We expect that you will, on the active methylene position, we should get an anion here. And that if you treat with, you know, that if you treat with a double bond here like this, with a double bond here. So this is a conjugated system. So conjugated system. Now notice this one. This carb anion is something which is, very strong nucleophile. Reason being it is always under resonance. So it does not have a very strong electron density. So it usually do not prefer 1,2 addition. So it will go for 1,4 addition. And since it goes for 1,4 addition, this double bond O, this double bond O will remain. And from here, it will start connecting to one carbon here, carbon 1, carbon 2, carbon 3. So, and then double bond O like this. So this is how the addition will take place. Correct? So this type of an addition is what we call it as the Michael's addition. Okay. I hope this part is clear. Right. Similarly, few more examples. Other conjugate addition. Other conjugate addition reactions. See other conjugate addition reactions if you notice. Suppose I have some R group, a double bond here, then a double bond O, and some R dash group is there. And I'm treating this with Br2. Okay. If at all I react this with Br2, in that case, we will notice that hardly much conjugation will take place. You will have one Br getting added here and one Br getting added here. Correct? Correct. So here, less rate towards towards 1,4 addition. Conjugate addition is less observed here. Rather, it will only go for an alkene addition, simple alkene addition. Okay. So, but if you notice some nucleophiles which can directly make an product attack here. So let me show some examples here. Suppose if it comes to example here. So Et2NH. Okay. So this, if you treat with any conjugated system. Now another important part is it always has to be aldehydes and ketones? No, even in the case of esters also, this reaction is valid. So if you treat this around 100 degrees Celsius, correct? So you would notice that you will have this double bond OET will be the same, but at this position you'll have N and ethyl and ethyl. So this is a 1,4 addition. This is proper 1,4 addition. Okay. Similarly, if you have methanol when you treat with a conjugated system, let's say a conjugated aldehyde here. So in that case, the product what you will get here is MEO, sorry, the same compound like this double bond O and H and OME. Let me show the mechanism just in case if you are not able to relate how is it exactly happening. See, double bond is here. Methanol's lone pair is the one which will try to attack here. This bond will move and this O minus will come. And this O minus is the one which will take the H plus away. And that's how you will get double bond OME and OH and this compound. And that on tautomerism, this OME will remain. And here you'll have double bond O and methyl like this. Okay. So what we get here is beta methoxy ketone. All right. So here it is aldehyde. So I'll put it as aldehyde only. Beta methoxy aldehyde. Same goes with thiols also. Another example. Thiols, let's say PHSH. That when you react with an aldehyde like this. So this is also a good nucleophile, but not something like a very strong negative charge on that. So that way, if it rearranges, the final product, what you will get here is this ketone will be the same, but SPH will be present. That is 1,4 addition. Got it? In case if you have HBr also, in case of HBr also, after addition here, so you will get this as Br here, double bond O here. This is the product you will get. Got it? So I guess you did understand, why in this case what will happen. Okay, how it works. Let me put another example which has been given. Suppose if I treat this with KCN and HCN with a group like this where you have a double bond here and double bond O here. So on addition, you will see that cyanide would be here, CN, and double bond O here. So this is found to be 78% yield, but the temperature condition that was given as 160 degrees Celsius. So as the temperature increases, always 1,4 is more relative. Okay, 1,4 is more expected. Clear? See few cases where you have actually, if the temperature slightly changes, what will happen? Okay, whether it will go for 1,2 or 1,4 addition. See, check this example here. Suppose if you have an aldehyde like this, and that in case if it I uh, on the arrow it was given like this, that first reaction is BuLi, which is a very strong base operating at minus 70 degrees to 20 degrees Celsius. Got it? Then second is H2O. In that case, now in such cases, definitely 1, 2 will be highly favorable. So you'll get this as OH and Bu. This is the connection that will happen. Okay. See one more similar example here will happen. Okay. So BuLi here. Suppose in case if you have NMe here. Okay. See, if you have a strong donating group like this, in that case, 1,2 addition is hardly going to be observed even with a strong nucleophile. So that's the reason why. In such cases, you would notice here you will always get 1,4 addition only. So this was 1,2 addition earlier. But in this case here, you will notice only 1,4 addition. So you will get this as Bu here with double bond O, NMe here. This way, this is the final product. So this is 1,4 addition. Got it? But if, see, same type of reaction, suppose if you have a double bond O and chlorine is given. See, chlorine is a strongly withdrawing group. So that's the reason if I react ammonia at room temperature, still it does not disturb the double bond here. It will go and convert into amine plus HCl. So here it is operating with a 1,2 addition. Because chlorine is a withdrawing group, it would not prefer to go for 1,4 addition. But in case if you have an ester, for example, like this, and then you are treating with ammonia here at room temperature, correct? In that case, you will see 1,4 addition is more favorable because OET is a donating group. Because it's a donating group, you will see this as NH2 here. Okay, and this time you will get this as 1,4 addition. So keep that in mind. If on C double bond O, if there is withdrawing group, then this is what will happen. So order of order of conjugated addition, if you have to compare, right? So definitely in that case, you'll have double bond O, NH2, this is the strongest, Nr2, that is the strongest, and then in that we'll have NHR or Nr2, NH2. So this and this. So here this is NHR here, or here it is NH2 here. So this is the order, and then if you notice we will have this as ketone here. This way we'll have ketone. Sorry, I mean ester. First ester, OR, then ketone here, then aldehyde, and the least comes acid chloride. So this is the order. This is conjugate addition order. Okay, correct. Notice as a important part, you can just take it as a note that the best nucleophiles doing conjugate addition, are thiols or thiolic groups. So if you have any thiolic groups, that will give the best nucleophilic addition here. Okay. For instance, if you have double bond like this with here double bond, and then I treat that with pH SH at 25 degrees Celsius and prolongedly keeping it for 5 hours, what has been noticed is that you will have this keto form the same way, but here you will have SPH. So this is product, and it was found to be 94 percentage. So that is the confirmation to understand that there is a very good nucleophilic nature there. Okay. So when it comes to hard acid and hard base concept here, correct? So that is uh, observing at which position we are getting the nucleophiles best, whether it is 1,2 addition or 1,4 addition. So to explain this part, what we can do, we can explain it through the theory hard and soft, hard and soft nucleophiles, hard and soft nucleophiles. What are hard and soft nucleophiles here? See, a hard nucleophile, let's say X minus is there, correct? Or I can say just X if this is X here. So usually hard nucleophiles are those which are small in size. Generally, if they are small in size, okay. And next, they are charged. That means they'll have minus charge usually. Got it? Next, they are highly basic, highly basic. Okay, or HX is weak acid. Correct. So that makes it highly basic. Next, it would have low energy, low energy homo orbital. Homo orbital is low, but uh, it will always like to attack polarized bonds, C double bond O. Okay, best examples if you see RO minus, correct, NH2 minus, okay, H minus, Me minus, Li plus, or anything like pH Li here. So these kind of cases. These are all going to be hard nucleophiles. Okay. On the other hand, if you notice what are soft nucleophiles, let this be Y. Okay. So they are generally large in size. Correct. They are mostly neutral charged. Correct. They are not basic enough, not basic because HX is strong acid. If HX is strong acid, this has high energy, homo orbital. Okay, and like to attack it, like to attack saturated, saturated or unsaturated carbon. Examples: Rs minus, I minus, R3P. Correct. So these kind of cases. HS. Sorry, I told you. PSH here like this. So these are all going to give you more of soft nucleophilic character. Got it? If I put all of them in order, right? If I put all of them in order, so you can just take this as a table. It will be easier for you to realize in all other questions also. From here, you can see the list of it. Hard nucleophiles. Then we have borderline nucleophiles. And then we have soft nucleophiles. Correct. So you would notice F minus, OH minus, RO minus, SO42 minus, because it is connecting from oxygen end. Okay. Cl minus, H2O, ROH, ROR, okay, RCOR dash, ammonia, RMGX, RLI. Okay. Now you might wonder, sir, these are all neutral forms. Then how will it give? So in the case of neutral forms, it is more temperature control. So if it is at lower temperature, they will act like a hard nucleophile. Sorry, yeah, hard nucleophile and give 1,2. Otherwise, they'll give 1,4. Okay. Next, borderline cases. They give both and highly temperature sensitive. So Cn minus, secondary 1 degree amine or 2 degree amine like this. Okay, or Br minus and so on. Soft one that includes I minus, Rs minus, RSH, PSH, correct, RSR, right, RSE minus, right, R3P, correct. Only alkenes, only benzenes, or simply call it as arenes, or only double bond, any C double bond C cases. So these are all soft nucleophiles, correct? So you can always apply this factor and you'll be able to get the answer. Got it? Let me show you with some examples. First one, if you have OMe with double bond O and double bond here, so this is a conjugated ester, and that first reacting with pH CuLi, pH to CuLi in the presence of MESiCl, Me thrice SiCl. Second, we have H plus and H2O. Now, minute the alkyl group is alkyl or aryl group is connected to metals like copper, which has high polarizing power, then the nucleophilic strength will decrease, and you'll only notice that we will be getting more of 1,4 addition. So you'll get this as pH double bond O, and you'll get this as 1,4 addition. Got it? Okay. Same way, if you have double bond O and H here and double bond, and second case, you see first I have Bu2Cu Li, right? And second we have H plus and H2. So again it will give 1,4 addition. So CHO. So this is 1,4 addition of butyl group. Done. Now, a lot of time question would be asked like, sir, why are we using this trimethyl silyl chloride? Let me show you through the mechanism once. Okay, what might be happening in the mechanism? See, in the mechanism, you will notice that when you have Cu minus and let's say pH and pH, this is how it is connected. And then we have double bond here, double bond O here, conjugated part. So we know that the nucleophile from the carbon will attack here, this pi bond will move, this oxygen will move. That is how the initiation happened, reaction initiation. Got it? So that will give you, sorry, not from carbon, from phenyl. So from phenyl, it will attack here. Correct. Overall, it was minus. So phenyl will take away the electrons and convert into this part. Okay. So what do I get here now? So what I will get here is that we will have O minus double bond, and then we have pH group added here. And this O minus is the one which will react with that silyl group here and remove that chlorine out. And that we will get pH double bond and O silicon with methyl thrice. Got it? Now, of course, Cl has gone from here. So now once you get this form, no, beta, you all you need to do is do hydrolysis. And from here you will make an acidic hydrolysis. So on adding with H plus, so this entire group will get this as OH plus here, OH plus here, correct? So that OH plus will make the silyl to come out more easily because that's a very stable carbocation. That is very stable carbocation. So as it becomes stable carbocation, now you'll get this as OH plus Si Me thrice with plus. And then this compound which has been formed will get tautomerized. And then we'll get double bond. Sorry, one carbon missing. Double bond OH. Okay. And of course, since you added water, this will react with water, convert into an alcohol form. So SiMe thrice with OH. So I hope you got an idea of the mechanism why that trimethyl silyl chloride is used. Any doubt? Please check. Right. Let's use that logic and try to solve these questions quickly. Whenever you have CH3, CH3 is a very strong nucleophile. So since it's a strong nucleophile, you will not make 1,4 addition. You will only do 1,2 addition. So you will write this as OH and methyl. So that is a product. So it is 1,2 addition product. Got it? Okay. Next, if you have PHLI, right? Next, pH minus is also very strong nucleophile, so that will also give you 1,2 addition. So we'll get this as OH phenyl here. So that is also 1,2 addition. But notice something here. It is the same Grignard's reagent, but with CUX. With CUX, the nucleophilic strength will become weaker. So that's why now we will not have any other alternative, but you will see that here double bond O, and on this position you will have R group here. So that makes it 1,4 addition. The next one is also same. Directly copper complex is given, so that makes it 1,4 addition. So this is also 1,4 addition. And next one R2CD. R2CD is even dangerous than this group R2C1. So you'll get this as R. So this is already 1,4 addition. Done. These are all the 1,4 addition, guys. Okay. In such reactions, no, normally temperature is not mentioned. You should understand that these are all operating at a nominal or normal temperature, room temperature maybe. Okay. Done. Right. This ends the next part, which is the application of tautomerism. Now we'll come across two very important or very exclusive type of reactions. One is called aldol reaction. The other one is canism. Okay, let me quickly take you through this. Aldol is about an aldehyde or a ketone group with an alcohol also present on. But the alcohol should be present always at the beta position. So that's why it is called beta hydroxy aldehydes or ketones. So you can see this is beta hydroxy ketone. Beta hydroxy ketone. This is also beta hydroxy ketone. Okay. So these are all aldol. Usually the reaction of aldol, to preparation of aldol is based upon two aldehydes reacting with each other, two ketones reacting with each other, or one aldehyde, one ketone reacting with each other. Okay. So one must have at least one alpha hydrogen to make this reaction. One must have at least one alpha hydrogen. Medium, acidic and basic medium are more favorable cases here. Correct. And the steps which are involved through the reaction mechanism, you will observe that tautomerism, enol-enolate ion formation, a nucleophilic addition reaction, and aldol is formed, and then a condensation will also happen. Condensation as in where you will have sorry, condensation as in where you will notice that uh, water has been eliminated out of it. So in case of this, water will also be eliminated. So yeah, these are the basic ideas we should have about how the reaction takes place in this case. Now let me show you by mechanism one by one how do we need to solve these kind of questions. So check. First, what is the overall reaction? Okay. So overall reaction is uh, 2 moles of CH3CHO. I'm taking first the basic medium, everybody. 2 moles of CH3CHO. When you react with a dilute OH minus. Okay. So in that case, the final product what you will get here is CH3, CHOH, and CH2, CH2, C double bond OH. But this on heating, right? By chance the heat is also given, then you'll write the overall product as alpha beta unsaturated aldehyde or a ketone. Correct? So this is the product. So this is called aldol. This is condensed aldol. So this is condensed aldol. Done. So this is the overall reaction. Now let's check mechanism one by one. Each step. The first step. CH3C double bond OH. If you treat with OH minus, so it will form first an enolate ion. So CH2 minus C double bond OH. This is what has been formed. This enolate ion will be in conjugation as CH2 double bond C, O minus and H. So both of these are enolate ions. Enolate ion. Okay, just these two are resonating structures, but both of them are enolate ions. Okay, second step. Now, if you have CH2 minus C double bond OH, okay, plus CH3 C double bond OH. Clear? In that case, this is the slow step of the reaction or the rate determining step here, wherein this CH2 minus will go attack on the second mole. That way you'll get CH3 CO minus with H connected with CH2 C double bond OH, correct? And this will take H plus from water, right? This will take H plus from water, and then it will convert into CH3 CHOH, and then CH2, then C double bond OH. So what we got here is beta hydroxy aldehyde. So this is an aldol. So what we got here is an aldol. Okay. Third step is about condensation. So that means once you take this aldol form here. Now notice something very important here. So wait, let me make this arrow smaller. Yeah. Now let me show you something important here. So this OH minus is a very weak leaving group, correct? So now when the OH minus has been, when you react with OH minus, that, okay, yeah, ordering. So then CH3, CHOH, and then we have CH minus, and then C double bond OH, correct? So then the C minus will push it on heating and OH minus will be lost from here. This is what happens on heating. So that's how we'll get CH3, CH double bond, CH, C double bond OH. Okay. What do you call such type of mechanism? It is E1CV mechanism. So usually in basic medium, it is the E1CV mechanism which is most favorable. Okay. So that's how it will happen. So you can see first in enolate ion formed, correct? Then you can see where is it? From here the nucleophilic addition is happening, correct? Then once you get this OH here, correct? So on this O minus is attacked here. So again a carb anion is forming, correct? Condensation is happening. Aldol is forming, condensation is happening. Here this will show some tautomeric nature. So tautomerism is also observed. So these are all the key terms. So these are all key terms that has been observed. Have you noticed something? What was the essential condition here? The essential condition is it must have at least one alpha hydrogen. So if there is no alpha hydrogen, something like formaldehyde cannot give you redox aldol reactions. Got it? So go through it quickly. Got it? So I'll also write that synopsis here in base catalyzed mechanism. See, in base catalyzed mechanism, okay. First, carb anion or enolate ion formation is observed. Second, you will be noticing that there is a nucleophilic addition reaction, which is NAR. Third, we will have E1CB mechanism observed. Mechanism for condensed aldol. Right. So these are the three essential features. I think I have written it there. Right. Sorry. Please check. Okay. Quickly go through it once, everybody. If you understand the mechanism, then it becomes easy to solve the questions. Let's see how the reaction works in the case of ketone here. Yeah. First, step, we have CH3, C double bond O, CH3 here, reacting with OH minus. So it will take H plus, converts into an enolate ion, CH3C double bond O, CH2 minus, and that enolate ion will react with the next molecule, which is CH3, C double bond O, CH3 here, correct? So as this CH2 minus attacks on this position here, so that will become CH3 here with, I'll put it this way, CH3 with CH3 here with O minus, and this connected carbon is CH2. One second. Sorry. So next, this CH2 will be connected with C double bond O CH3, correct? So this is after the addition which you will get, correct? Okay. So normally in this case, when it comes to the ketones, the first step will also, always compete with the rate determining step. So the first step as well as the second step, both of them are rate determining step. Yeah. But mainly when it comes, sorry, first step and second step both will compete with the rate determining step. But the second step would be much harder because this is a very bulkier substrate here where nucleophile has to go and get added. So that becomes a very challenging step here. Got it? And notice once you get this form here, the second step here is to first get uh, second step here is to first get protonated and convert into an enol form. So that will convert into CH3. Okay, CH3. CH3 and CH3, and then we have OH, then CH2, C double bond O, CH3. Correct? From here again you will have the same step, correct? So we need to on heating it, see, as soon as you heat it through E1CB mechanism, elimination would happen and you'll get this as double bond CH, C double bond O, CH3. So this is the product you will get. This is the condensed aldol. Okay. So read out something here. That is, the first step is not the RDS. We can use anhydrous conditions to avoid the reversible reaction in first step. Because in the first step, OH minus will take H plus and water will increase. So which means if you take a dilute solution, the reaction would be always more on the left hand side. So if at all you want to make the reaction to go more on the right hand side and make a less amount of water content so that the reaction would be pushed into the forward direction. In such case, try to take more often anhydrous condition. Okay, clear. Second step lies mostly in the backward direction because this is extremely difficult to make this nucleophilic attack. So if only you increase this enolate ion, then the reaction can go more forward. And removing the product would always help in making the reaction forward direction. Because as soon as the product is formed here, this product is formed, this will always go backward direction back to aldehydes or ketones. So it's very difficult to get any sufficient percentage of aldol here. That's the reason why to increase the product, you will be continuously distillating the product that has been formed. And to use this, we use something called a Soxhlet apparatus. A Soxhlet apparatus is something where we take the vapors and continuously remove these vapors in the reaction. Okay. So to make this reaction faster, what we can do, we use an anhydrous catalyst, something like barium hydroxide powder on hot acetone. So acetone is the reactant on which if you use barium hydroxide powder and heat it, then the reaction would happen faster. Got it? So I hope you understood the base catalyze mechanism in the case of ketones. Okay. Now let's see acid catalyze mechanism in the case of ketones. Correct. In the case of ketones, how the acid catalyze mechanism will take place. See, if only I have a ketone here and react with one more ketone here in acidic medium here, right? So let's say dilute H plus here. So this would give us an enolate ion. First I'll write the overall product. Overall product, what you will get here is like this: double bond O, sorry, here, 1, 2. I'll have to put OH also here, and then I'll have double bond O like this, correct? This is the aldol, and in case if you are heating it, so definitely you'll get the product as this conjugated form of a ketone here. So this is the product formation. Got it? But see, what will this do to avoid the reaction to go more in the reversible reaction? Instead of taking dilute H plus, what we can say, we can take dry H plus. Dry H plus, you can get it as dry HCl. Okay, so let me write down this as a note. To avoid reaction, to avoid reversible reaction, to avoid reversibility in first step, use dry HCl instead of aqueous H plus. So that will help you out. Okay. So you first get a 3-degree alcohol here, correct? And once you get a 3-degree alcohol, it is very easy to make a proton here. Okay. So therefore, if you have a 3-degree alcohol, let's say this is how the product is: double bond O and alcohol, 3-degree alcohol, and I'm using this 3-degree alcohol still present in acidic medium. So you would notice that it is easily going to get protonated. And on a 3-degree position, right, even just at a room temperature, it can easily convert into a carbocation. So that water will go away, right? H2O will go away and carbocation will form. So once you get a carbocation formation, right, it is easy for water to extract this proton and push it here and convert into a double bond. So a lot of times here temperature is not mentioned. Even if the temperature is not mentioned, we know that it can easily get eliminated. Hence, this will be the product is called as mesetyl oxide. The common name is mesetyl oxide. The type of mechanism that is happening here is E1 mechanism because it is completely getting converted into a carbocation form. So you can see in acid catalyzed mechanism, an E1 mechanism is observed here. This is how the product would come across. Now notice some examples in this case. For instance, if you have 2 moles of acetone used, 2 moles of acetone used and using dry HCl, what is the product you will get? See, I have not mentioned heat, everybody. You should understand that by default the elimination would happen here. So you will get this as double bond O. We just learned it. This is mesetyl oxide. This is mesetyl oxide. What if I take 3 moles? So 3 moles of CH3, COCH3. See, when I take 3 moles in the same dry HCl case, the same dry HCl case, first of all, this side the mesetyl will form. And again from this carbon, it will attack onto the next molecule. And that's how you will get one more double bond here. So 2 moles. Okay, let me show you how it is happening like this. If you have a double bond here, and this side from enol attack will take place. So in on a ketone here, double bond O like this. So this is the enol form here on the right hand side. This will push here, pi bond will attack here, and thereafter elimination will take place. So this is a 3 mole group. So this is called forone. The common name is forone. This is called forone. And by chance, if at all I take 3 moles of CH3, C double bond O, CH3 taken, but instead of using dry HCl, what if I take concentrated H2SO4? Concentrated H2SO4 typically gives a cyclization here and converts this into a product called mesitylene. This is called mesitylene. Got it? So this is how the reaction would take place in this case. Okay. So imagine, I mean, something like this. We have, a ketone here, CH2 double bond COH, and sorry, CH3 here, CH3 here, and OH here, correct? And H is here. So similarly, one more molecule H is here, CH2 double bond COH, and another, I mean, double bond here, and CH2 is here, like this. Correct? Sorry. Here, C CH double bond. C, not CH2, CH double bond. It is CH double bond, CH3 is here. Same way here also I have double bond, CH here, and OH is on this side. Imagine OH is on this side, and CH3 is here. Correct? And in a typical way, we have one more OH here with C double bond OH with CH3 and double bond CH2. Okay, I'm just trying to pull this slightly away from it, like this. Yeah, let me put all of these together here like this. Okay, now let me show you how this is happening. So this we have H here. So imagine removing water molecules from here, water molecule from here, and water molecule from here. Okay, so when you what happened? Where? So after removing that, you will see there is a cyclization happening. Oh, 1, 2, 3, 4, 5, 6. So these are the 6 carbons which are connected like this. So that becomes the benzene and becomes mesitylene. Okay. So this is how you will get a mesitylene form in this case, everybody. Okay. So please quickly check out the acid catalase mechanism. Okay. Be back in a minute. Look into this. What are the types of aldols we will come across? First one is self-aldol. Self-aldol is when you have two moles of the same molecule and trying to form an aldol. Let me show you the shortcut how you can do. See, when you want to make an aldol, first write the structure the way it is given. So, see how I'm writing CH3, CH2, then CH. Instead of O, you write that as OH. That's it. That is a trick. And now you write the second molecule. For second molecule, write a bond here. Then check out this alpha carbon. Please write down that alpha carbon directly here. So that means it will be CH and CH3, and then we have C double bond OH like this. That's very easy to write if you understand that point. Okay, clear? And this on heating, because you're heating also. So what do I get? This entire molecule where OH will be removed out, correct? And in this case, H will be gone, OH will be gone from here, and you'll get a double bond here. Now notice one thing. If the question is asked how many aldols are formed, notice one thing, here there is a chiral center, here there is a chiral center. So I can say 4 stereo product of aldols. Okay, so there are 4 stereo products of aldol. Come here now. If the question is asked what about the condensed aldol, so we can say 2 stereo products of condensed aldol. Condensed aldol. Okay. Or if the question is directly given, like, heat is given and you were asked what are the final total products, you will always notice this one. So you should always write there are 2 stereo products. Okay. If without heat is given, you will stop it here and you will express this as 4 stereo products. See the second one also, everybody. So requirement is what? There should be one alpha hydrogen, which is there here. So since there is one alpha hydrogen, I can say this as here like this. Okay. So I told you the trick here, what I can do. Where there is CH, you make this as OH there. And then connect it with the same alpha carbon here. So if you connect that, there will be one methyl up, one methyl down, and then here. And after that, we can get this as CHO or C double bond OH. C double bond OH here. And now this is interesting. On heating, it will not do anything because this side, it is a secondary alcohol. To remove this, we require some strong even CV mechanism. Even CV is not happening because there is no alpha hydrogen here. Since there is no alpha hydrogen here, further elimination product you should not have to be reported. Okay, no condensed product. Correct. Since see, if the condensed product is not coming, right, this will yield will be very poor. So very poor yield. So reaction will be highly reversible. Okay, it might find some alternative route, something towards a Canizaro, which I'll explain. But otherwise, it is a very poor yield in this case. Okay. Number of stereo products are two in this case because there is one chiral center. Check out the second case here. So we have, a ketone here like this. I told you one group you make it as an alcohol, and from the second group you connect it from the alpha position and make it into double bond O like this. That's it. So this is the aldol. So you will get one chiral center here. So there are two stereo products. There will be two stereo products, and that stereo products on heating, the molecule will convert into a double bond form here. So this molecule can be released out, and I will get this as a double bond here, this way, say, and double bond O. Okay. Now, since there is no cis and trans product here, so one product, only one product that is optically inactive. Then that is a product. Check out the fourth case. This is a ketone. So ketones are very poor yield in the case of basic medium or aqueous basic medium. That's why we took a solid barium hydroxide. So using that, what we can do? So we can have like this. First, an alcohol will be here down. Sorry. First, we can have an alcohol up, a methyl down here, and that is connected to next molecule. So we can have this as, now this is interesting. You can make a connection from this end also. You can make a connection from this end also. So we can make a connection from this end. So we can get this as double bond. See. So once you get this product here, I'll get one chiral center. This is one product. You can do the same thing from this end of the methyl group also. So which means from here, let me write down that case. From here, you can actually attach from this end also here. Correct. So if I attach from this end, it will also have a methyl group. Then we'll have a double bond O and CH3. So this time we'll have two chiral centers. Okay. So the number of products formed will be two stereo products here. You will have four stereo products here. Four stereo products here. See, if nothing is given and you need to decide which is major product. Just a minute. Okay, now. Then if you want to make an aldol here, then you can make it as a double bond here, like this. This is one product, and the other product will be double bond this way, methyl here, and another double bond over here, this way. This will also have a cis plus trans, and the last one, this will also have cis plus trans. Okay, so here also we get four products here. So two stereo here, two stereo, and two stereo. In this case, two stereo here and four stereo here. Total six aldol products and four condensed aldol products. But listen, everybody, how do we decide which is a major product? See, for that, you need to do only one simple thing. You check out which side is a double bond more stable. Is it this side or this side? Since the double bond enolate ion is more stable here, this is called thermodynamic enolate ion. This is thermo-enolate. If you have this as this one, this is kinetic enolate. So thermodynamic enolate is more favorable because you are making the reaction with some heat. So whenever the heat is being given, it is always favorable in thermodynamic way. So therefore, this will be major as an aldol, and this will be major as aldol condensed product. Then everybody, simple term, when you have two different types of alpha positions, you need to check out based upon the stable enolate form. Okay, that stable enolate form will give you the major product. Done. I guess all of you understood the self aldol case. Now notice the cross aldol form. If you have two dissimilar aldehydes or ketones, so one aldehyde here and one aldehyde here, so two different aldehydes. So we can have basically self product as well as the cross products. Okay. So we can always have self also. First, let me write down the self form. Everybody look carefully. For this molecule, I'm writing the self form. So self form is CH3, CHOH. Then we have CH2, CHO. This is self. Second, I'm writing the self for this one also. Sorry, self for this one also. For this molecule, it will be CH3, CH2, then CHOH, and that is connected to CH3, CHO. So this is also self. Now let me write the cross ones. That is, this CH2 minus going attacking here. That is the first thing I'm writing. Okay, focus it. So that means I have CH3, CHOH, and then CH3, CHO. Last one. Now this side, this CH2 minus attacking on this CHO here. So I'll have CH3, CH2, CHOH, and that is connected with CH2, CHO. Okay. So check, this is a chiral center here. This is a chiral center. 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 Here, only one chiral center. Okay. So how many aldol products, everybody? So this is 2 plus 4 plus 4 plus 2. I'll write on that here. So 2 plus 4 plus 4 plus 2. So total 12 aldol products you will get. It's an important JEE question. You will be asked like how many total number of aldol products forming. So answer is this. Now let me write all the condensed aldol form. So after elimination. So if I make an elimination here, what do I get? I'll get CH3, CH double bond CH CHO. Second one, CH3, CH2, CH double bond C, CH3 and CHO. Third one, CH3, CH, double bond C, CHO and CH3, and here CH3, CH2 and CH, double bond CH and CHO. So again, with respect to this position also, I can have cis and trans. Here also I can have cis and trans. This stereogenic unit also have cis and trans, and this will also have cis and trans. So that makes it total of 8 products. So 2 plus 2 plus 2 plus 2. So that make it total of 8 products. So guys, whenever you have this kind of case where cross aldol need to be found out, so you just need to check out how many chiral centers, how many double bonds are present. Okay. Any doubt here? Check. Now, I'll take one more case. What if you have HCHO and CH3CHO? Okay. This is also a crossed aldol. In such cases, see, in these cases, sorry, first let me go here. In these cases, it is very difficult to say which is major because all of them are sufficiently formed. They don't. Do that. Check this out. The self of this is CH3. Self of this is CH3, CHOH, CH2, CHO. For this is a self aldol. There is no self aldol for formaldehyde, but there is a cross aldehyde. That means for this position, this CH2 minus can go and add. So I will get this as H, CH, OH, CH2, CHO. Only these two are possible. One is self here, the other one is cross. But remember, whenever you have such cases where there is no alpha hydrogen only, something like formaldehyde, compared to acetaldehyde, since this is more reactive, you will always notice this is major product. So always report the major product as a cross product only. You'll always report major product as cross product only. Another example, suppose if you have PHCHO and I'm treating that with CH3, CH2, CHO in the presence of OH minus and heat. So again now pH, OH, and this will connect as CH, CH3, CHO. So I'm writing only the cross one. See, cross one is a major product. So of course, because the heat is given here, so I will write pH, CH, double bond, C, CHO, and CH3. So this is major product that you will report. Similarly, here also after the cross product here, after the elimination here, so I'll get this as CH2, double bond CH, and CHO. This is called acrolein. This is called acrolein. So acrolein can be created out of the cross product from formaldehyde and acetaldehyde. Okay. Is this point clear, everybody? Now notice next type of reaction where it is intramolecular. That means within the ring. Within the ring, always follow this point that give priority to first 6-membered ring formation, then to 5-membered ring, then 7-membered ring, and then 4-membered ring. So ring chelation will overpower any other stability factors. Okay. So just try to follow this part. So you can see 1, 2, 3, 4, 5. So from here, the only chance I have is attachment of this to this or this to this. Both will lead to the same thing. So what is the ring size? 1, 2, 3, 4. So I'll have a 4-membered ring size here where we will have H, OH, and that 4-membered is connected to that we will have a double bond O and H. Okay. So by chance, if heat is given, in that case, I will write this as a double bond here and a double bond O and H here. So this is the condensed product. Okay. Next one with heat is given here. You can see 1, 2, 3, 4, 5, 6. Of course, the 6-membered ring should always be preferable. So it will be 6-membered ring. On this position, we have OH and H. And from the position where it is connected, on the 5th position, we have a ketonic group. So this will not be stable here. It will immediately convert into double bond O. So this is a product you will report. See the next case. Again, you have 1, 2, 3, 4, 5, 6. 6-membered here. If I go from this end, that is not correct. If I go from here, that is not correct. So again, I'll have a 6-membered ring here like this with OH here, OH and H here. Clear? OH and H here. And 5th position, I have a double bond O. And 2nd position, I have a methyl group here. That's it. And from here on heating, you will get double bond on this side. So I'll get double bond here, double bond O here. So this is a product. Next one, both sides have ketone. If at all it attached from here, 1, 2, 3, 4, 5, 6, 7, a 7-membered ring. If at all it attached from this alpha position, 1, 2, 3, 4, 5, a 5-membered ring. Between 7 and 5, 5 is preferable. So you will have this as H and OH form here. And the molecule where it is connected, it will have a C double bond of CH3 outward. This on heating will show double bond here, conjugation outside this way. Intramolecular with one ring and one open chain here. See, this is a keto form. And usually the cyclic ketones are more reactive than a straight chain ketones. So you do not attack anything from this to this here. You always make a reaction towards cyclic ketone. So I can make an attachment from here 1, 2, 3, 4, 5, 6. So it is already making a 6-membered ring. So this way, it is a 6-membered ring. At this position, we have OH, correct? And from the molecule where it got connected, that molecule already have a double bond O here. So like this, I have a double bond O and methyl. And because on heating, what do I get here? On heating, we can get a double bond at this position and double bond O here. So this is a final product what you will get, right? And this case, see C5 onwards. Why? Ring size again 1, 2, 3, 4, 5. This is the alpha position, so it will make a ring size. In this case, there is a compromise. That is, it will now turn into a 7-membered ring like this. And on the other side, we will have a 5-membered ring like this way. Okay. Oh, sorry. Connected group like this, right? So it is 7-membered ring and it is connected to this with a 5-membered ring formation like this. Okay. So this is between 5 and 1. This is 5 and 1. Okay. And adjacent to 5, we have a double bond O. And here we have an OH. And that on heating will convert into this form. So a double bond here, double bond O here. So this is the final product. Next, see, what if I make an ozonolysis first? So ozonolysis will bring this ring to be without disturbing that ring. You will have a CHO here, CHO here, and another CHO here. So we can make a intramolecular aldol if you OH minus is continued in this reaction. So that means from this position it will attack here. So what is the ring size? 1, 2, 3, 4, 5. So 5-membered ring like this way. And Here we will have an alcohol, and this position we have a CHO. And that on heating will give double bond and CHO. So this is the product formation. So quickly go through all the intramolecular, everybody. Just take a minute, check out properly. Right. So the next one is Robinson annulation. Annulation means ring formation. Let's see here how the ring is forming. First, you need to have a ketone. Okay. That will make a Michael's addition first, which means there should be 1,4 addition, a conjugate addition. Then conjugate addition should be followed by intramolecular aldol. I forgot to write that intra aldol. Okay. So let me show you how is this working. Suppose as soon as you react with base, you will get an enolate ion. And on the enolate ion, you will see the double bond O this way. So that gives you a carbon anion to attack on this position, make into an conjugate addition. So as soon as it gets into a conjugate addition, we'll have 1, 2, 3. Here we'll have a double bond O here. I mean O minus here first. Double bond like this. Okay, so this get tautomerized in water. So that will convert back into ketone. Double bond O this way. Okay. Now you can see once you get this molecule, once you get this keto form here, check out the ring size from here. Check out intramolecular case here. So 1, 2, 3, 4, 5, 6. So which means as soon as you take this compound and react with base again, because it is anyway in basic medium, so the OH minus will take H plus from here and it becomes an anion like this with minus, and that minus will go and attack on this carbon, making an intramolecular aldol. So as soon as the intramolecular aldol is done, so you will have a 6-membered ring here this way with OH, and from the connecting group adjacent to that we will have a double bond O, and that on heating, okay, that would convert into a double bond here and double bond O here. So this is the product formation. Please check. This is Robinson annulation. That is a Michael's addition followed by intramolecular aldol. Okay. Next one. Next one is nitroaldol. That is an aldehyde with CH3NO2 in the presence of dilute KOH. So NO2 is a very strong withdrawing group. So that helps in getting a carb anion here in basic medium. And it is that carb anion which reacts with C double bond O H. This goes, attacks here, and that will lead to the formation of pH C O minus H with CH2 and NO2. That on heating, finally I'm writing the product CH double bond CH and NO2. So this is called nitroaldol. Cyanoaldol, same logic again here also. So pH CHO plus CH3CN in the presence of dilute OH minus. So on and heat. So you'll get first this as CH OH with CH2 and cyanide, and that on heating we will get this as pH CH double bond CH and CN. This is cyanoaldol. Next, what is no-Winkel's reaction? So no-Winkel reaction is also very similar kind, but this time with an active methylene form. This is also a cross aldol, that is CHO. First, let me write down that here as an overall reaction. That plus if you have CH2, which is connected to strong withdrawing groups like ester. And this, when you react with ETO minus and heat. So what do I get? I will get this as PH, CH, double bond CH, sorry, double bond C, and this is COOET and COOET. This is a product formation. So mechanism wise, if you notice here, so I can simply say that as CH double bond OH where it is there. Now this CH minus, because you are taking ethoxide, so that will take away this H plus from the active methylene position, and this minus would go attack on this position, and thus giving us PH, CH, OH, and CH with ester group COOET and COOET. And this on heating, we will get as PH, CH, double bond C, and COOET and COOET. Now, here is interesting fact. I can actually continue this reaction from here. Please, up to this, the reaction is done, but I am continuing. See, what if the same reaction is being asked to hydrolyze first? On hydrolysis, we will first get this as PH, CH double bond C, COOH and COH, because they are ester. Ester will get hydrolyzed to form acids. And these acids, if at all I heat it simply, have you noticed that this COH and COH, both of them are at beta position to each other. And at beta position, if you have two acids, it will get decarboxylated. So you will get this as PH double bond CH double bond CH COOH plus CO2. The product what we got here is cinnamic acid. So to make the cinnamic acid, you can use this reaction. Clear? This is Knoevenagle's reaction. So all of these are very simple ones. The attack is what you, if you know that, it's very easy to figure out. Next one, retroaldol. Retroaldol means you already have an aldol, but on adding it to basic medium again, the reaction go to some new aldol form, right? For example, check out here. If at all I have given you this aldol, double bond O, double bond and ethyl. This is an aldol. But on reacting with dilute OH minus, correct? If at all it is going to some new aldol here. So the new aldol is like this. So double bond, okay? Sorry, my mistake. It is making into a new aldol form. The new aldol form is like this. Double bond, ET, and then we have double bond O and CH3. Got it? Yeah. And from here, eventually it will form into dilute OH minus to finally get into a new aldol, which looks like this. Methyl here, double bond, another methyl here, and double bond O. So you can see from this aldol, you are going all the way to this aldol. Okay. So if one aldol is converting into other aldol, it is called as retroaldol. See, how does it work? You basically need to make a reversible reaction, come back to the original ketone, how it was. This is how the original ketone was. Let me show you how you can get it. So from here, what are all the retro steps I need to take? So from here, check out. What must have happened to get this form here? Heat must have happened. So before heating, this must have been a double bond O. Here there must have been a hydrogen. Here ethyl and OH must be present. Because aldol is a beta hydroxy, this is the only thing you can expect. So for this to happen, probably there was a carb anion which was attacking to make this, correct? So which means there was an H2O here, which was making it into an O minus form. Okay, so this was an O minus form. And this O minus must have been a keto form here, like this. It must have been a keto form where this bond must have been a carbanion form. So this is what must have happened in the presence of OH minus. That is, here we have C double bond OCH2 minus. Okay, and here there must have been a sorry, here this group here. So there must have been a double bond O and ethyl, correct? And this must have been come from OH minus, correct? Where we have this CH3 group on this end. So this must have been CH3 group here like this. Okay. So can you notice that this group and this group is same? So this is how originally it must have been present. Now I'm trying to find out an alternative path. This was one path of aldol formation. What is the alternative path here? See, check out. This I can write it as there are 2, 3, 4, 5, 6, 7 carbons, right? So let me write down this 1, 2, 3, 4, 5, 6, 7. Right? So 1, 2, 3, 4, 5, 6, 7 carbons. So one ketone is here, the other ketone is here because the other end it is ethyl. Now I earlier what has happened is this got attached here. Now I could have done this one also. Beta got attached here. These two could have been happening. So now this time in basic medium, let us continue to make the addition on this end. So as you do that in the presence of OH minus here, what is the ring size? 1, 2, 3, 4, 5. Now also it is a 5-membered ring. It is a 5-membered ring. Here we have OH and methyl. The group which is connecting is also having a methyl. Adjacent to that, we have a double bond O here. This is the way it is. And now on heating, what do we get? On heating, we will get this as a double bond here, methyl, methyl, and double bond O. That is a product formation. Right, everybody? Please check. This is how you need to work for aldol. Right. So please check. I want you guys to try out one. Okay. If at all aldol is given, go to the retro form. Example. What if it is given this way? I have a double bond O here and I have phenyl group here and a double bond here. And this was being treated with dilute OH minus. Please figure out what is the aldol you can get, everybody. See how I worked out on the steps in the earlier question. Try to do the same thing here also and get it. Right. So the product you're supposed to get in this case is this one. Okay. Where we have double bond pH and then double bond O. Okay. Check if you have got this. I'll put some steps here. One step would be about writing H here and OH here and pH here. Okay. Then after opening it up, After opening it up, it is basically ketone here. Okay, and this from here onwards. So I'm writing this as carbon 1, 2, 3, 4, 5, 6. On sixth position, I should have another double bond. Why? Okay, 1, 2, 3, 4, 5, 6, and then double bond O. pH here. This way. Okay. So 1, 2, 3, 4, 5, 6. Oh, sorry, there is one more methyl and pH here. Methyl and pH. So there should be one more methyl and pH here. So this time I'm making an attack from here to here. As it happens, again you'll get a 6-member ring, and here we'll have an OH and methyl, and from the connecting carbon that has a pH on it and double bond O here, and that on heating will convert into a double bond here, methyl here, sorry, phenyl here, methyl here, and then double bond O here. So this is the other form of aldol. Okay, so and aldols are interconvertible, correct? So from one side to the other side, it can keep moving. Got it? I guess you guys understood this part. How to get the retroaldol part, right?